Most saving institutions offer compounding intervals other than annual compounding. For example, a bank that offers quarterly compounding computes interest on an account every quarter. That is, every 3 months. Instead of computing the interest once each year, interest is computed 4 times each year. So if a bank advertises that it is offering 8% annual interest compounded quarterly, 8% is not the growth factor. Instead, the bank would use 8% divided by 4 equals 2%. So this part right here, folks, is really important that you understand where we're getting this from. If they do an annual 8% interest, and they're going to give you a piece of that each quarter, you're only going to get 2% per quarter, so that at the end of the year you've gotten all 8%. So 2% is the quarterly interest rate. What is the quarterly interest rate for an account with an annual rate of 5% compounded quarterly? All right, so again, in this case, it is saying quarterly interest rate. They're going to compound it quarterly. So what we're going to do is we're going to take that 5%, we're going to divide it by 4 because there's 4 quarters in a year, and that means that we would get 1.25% each quarter throughout the year. So that way, when we finish the year, we got our total 5%. Suppose that Margaret invested $50,000 in an account above. In the table below, determine Margaret's account balance after the specified times since her initial investment. All right, well, if it had been 3 months, guys, that would have been 1 quarter. So what would happen is you would have to say 50,000 times 1.0125 raised to the first power, because only 1 quarter has passed. And remember from our lesson yesterday, where we would get that 0.0125 is where we change that quarterly rate over to a decimal, and then we do 1 plus the rate. And if you put that in your calculator, we would get that that's approximately $50,625. Actually, I think it comes out to be exactly that. So what if it was 6 months? That would be 2 quarters. So then we would have 50,000 times 1.0125 to the second power, because 2 quarters have passed. All right, go ahead and fill out the rest of the chart. And when you get to the end where it says T years, then you're just going to write a formula. Pause the video, and when you're finished, start the video back. So notice we're doing the same calculations. The only part that's changing is the power up here, so that we don't have to do this over and over again, and we can use our technology to program this. It would be nice to have a formula. So we're going to write a formula where T is the years. But notice that when it was 4 years, we actually raised it to the 16th power because there was 4 quarters each year. So if we're going to do it for the T years, it would have to be 50,000 times 1.0125. But we wouldn't raise it to the T, we'd have to raise it to the 4T, because T represents our years, and there's 4 quarters each year. All right, so that's where it goes into number 3. Write the amount A in the account as a function of T, the number of years since the investment was made. So we're just going to take this last row of our column and just make it into a function. A of T is equal to $50,000 times 1.0125 raised to the 4T, where T is the number of years and A is the amount in the account after that many years. So then it goes on to say, how long will it take for Margaret's investment above to double? So what we want to do is let's make a little sketch of what's happening. And to make it easy, so that I don't have to write 50,000 and 100,000 on my y-axis, I just did it as my y-axis represents dollars and thousands, or thousands of dollars, and put the 50 and the 100, because we know a double 50,000 would be 100. And then we're just going to draw a sketch. We know that this is an exponential function that's growing, and you can see that after 4 years it's already to almost 61,000. And y'all, it doesn't have to be beautiful, just draw a little sketch of, you know, what would happen there. And then we want to know, when would that reach $100? So if we can program this in our calculator, we can find that intersection to answer this question. So going to our calculators, hit y equals, type in the function. The best advice I could ever give you is next go to your table, because by looking in the table, you can see about how long it would take to double. It won't give you exact answer, but we know that we're trying to reach 100,000. So we can see at 13 years, We're not quite there. 14 years, we've reached 100,000, and that helps us to figure out our window. So to graph this, we're going to go to our window. I'm going to real quickly fix my window. I'm going to hit zoom 6. It's not going to let me see anything, but it gets me back to that standard window because mine was kind of messed up. So then I'm going to go back into my window and manually fix this. I know the answer is between 13 and 14, so I want my X max to be bigger than that. Maybe you want it to go to 15, or heck, maybe you even want it to go to 20. I'm going to change my scale here to 2. And then my Y max, I want it to go higher than 100,000, so maybe I have it go to like 120,000. And I'm going to make my Y scale 10,000, so that way my Y-axis isn't too thick. And then graph this. All right, well, the problem is I forgot to go into Y equals and also type in 100,000 because that's the intersection that I would like to find. So let's go back and add that in there and hit graph. And remember, we want to find the intersection. So to do that, we're going to hit second trace, which is our calculate. We're going to go to number 5. We're going to scroll over by that intersection. There's only one of them, so it should work, but it's always good to go ahead and get that practice. And then press enter, 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 and it should give us the intersection. All right, so from our intersection, we got that it happens about at 13.95. But because this is being compounded quarterly, if it's 13.95, we'd actually have to round that up to 14 years. Because we have to look at each quarter. That money only is applied each quarter. Now, if this came out to be 13.75, we could have said 13 years and 9 months. But in this case, we have to round up because it was a little bit more than that. All right, part 5. How much less time is required for Margaret's initial amount of money to double when the rate is 5% compounded quarterly versus 5% compounded annually? Well, we already have our compounded quarterly answer. So to figure out our compounded annually answer, you're just going to go back into your calculator and program it using the annual formula. So in Y1, put in 50,000 times 1.05, because we're going back to our formula from the previous lesson. If it's just compounded annually, it's just 1 plus R. We don't need to divide that up. And then raised to the T, which in our calculator we'll put X. And then again, we want to know when that doubles, so then go in there and put 100,000, graph it, and find the intersection. So if you do that correctly, you should see that there's an intersection at 14.21-ish 100,000. So we'd say where X is approximately 14.21. Well, again, if it's compounded annually, you can't say 0.21 because it's not going to happen in the middle of the year. All right, so again, if it's annually, we have to round up to 15 years. So for compounded quarterly, it took 14 years. Compounded annually, it took 15 years. So you can see there's a difference of a year. And that's why it's important to shop around. The more they are going to compound your money, the better off it is for you, because then you're getting a little piece of that interest throughout the year, and you're not having to wait till the end of the year to collect any of your interest. And obviously, as you have more money in there, then the next time you're earning interest on that interest, not just the principal amount. So what is our compound interest formula? Pretty much all we have to do is take your basic percent formula. Y equals A times 1 plus or minus R to the T. And then we are going to, the A is still going to be the initial value, but we have to take that rate and divide it by the number of times it's being compounded. And then we also have to multiply the years by the number of times it's being compounded. Now, of course, we can use this formula for not just when it's years. You can have things that are compounded daily and whatnot. All right, so this is our general compound interest formula. Notice I put plus or minus in here because you can have situations where things are being compounded and it's a depreciation problem or decay problem. And all you do to fix that is if it's growing, you put plus the R. If it's decaying, you put minus the R. You may have seen this formula in past. Instead of them making it in functional form, they'll use the variables A and P, where P represents principal and A is just your final amount. It doesn't matter, guys. We know that we can change up the variables, so don't let that get you caught up. The biggest thing that makes this formula different from the previous lesson is we've added this in there. So anytime something's being compounded per year or per a certain time period, you've got to use this formula. So find the account balance after 20 years if $100 isn't placed in an account that pays 1.2% interest compounded twice a year. All right, so using our formula, we would start with our initial value, which is 100. We're going to say 1 plus. Remember, you always have to change this percent to a decimal. So the R right here would be 0.012. Move that decimal place 2 places to the left or divide that percent by 100. And then because it's being compounded twice a year, we would divide by 2. And then we also have to raise this to the 2 times 20. And I'm even going to take this y equals off because we don't need this. We're not even writing the function. We're just going to work this out. So using that formula from the front side, you always raise it to the nt. So if you want to clean that up a little bit, you can. The only thing I would say to be careful about is if you start to clean this up and it rounds, don't round it. I would rather you type it just like this in your calculator. This one comes out nice when you divide that. That's 1.006 raised to the 40th power. But if that was like a repeating decimal, you do not want to round that or you're going to be losing your money. And nobody wants that to happen. So if we put that in our calculators, pop it in, we get that that's $127.03. Okay, for the next one, I would like for you to set up the function or set up the problem and work it out. And then you need to write a function to be able to work out the second part. So pause the video, try it, start the video back when you're finished. Okay, some really important things to do with these. Make sure that you're rounding to 2 decimal places because this is money, so we should be rounding to the nearest cent. Also, make sure that you are including your units. So for this one, our initial value was $4,000. That's our principal. We want to find out the balance after 8 years, so T is 8. It is being compounded quarterly. That's how we know we have to use this new formula because it's not just done annually. So that's 4 times a year. We pop everything in our formula, pop it in our calculators, and we can see that after 8 years, they now have $6,143.56. So the next part. For this part, you have to actually write the function where the input variable is the time, because in this case, it's saying how many years would it take to double. So we do not know what the time is. That's the part we're missing. That's what we want to find in the end. So the formula is very similar to what you did in the last part. It's just that when you raise that to the 4 times 8, you're now just going to make that to the 4t. And for right now, we will be using our calculators. Later in this unit, you're going to learn how to solve these algebraically. But for now, we're going to use that intersection in our calculator. It wants the money to double, so if we started at 4,000, we're now at 8,000. When you find this intersection in your calculator, you get that it's about 12.92. Again, you have to remember that this is being compounded quarterly, so because that's more than a quarter, we got to round that up, and this would be 13 years. If we say that it would be 12 years, 9 months, the money actually hasn't doubled yet. So we have to look at each quarter. Next example. In 1966, a Miami boy smuggled 3 giant African land snails into the country. His grandmother eventually released them into the garden. And in 7 years, there were approximately 18,000 of them. The snails are very destructive and need to be eradicated. Assuming the snail population grows exponentially, write an expression for the population P in terms of the number of years T. That's worded wrong. The number of years T since their release. Okay. So what we have to do for this one is kind of go back to our basic formula of y equals a times b to the x. We know that he initially had 3 of these snails. He now has 18,000 of them. We don't know what the base is, but we know that 7 years has elapsed. And so if we substitute that in and solve for the base, we can write the function and kind of see what's happening here. So the first step is we would divide each side by 3, and we get 6,000 is equal to b to the 7th power. And then to undo that 7th power, we either need to take the 7th root of each side, or what to me is a little bit easier, especially when programming this in your calculator, is just raise each side to the 1/7 power. So when we do that, if you type in your calculator 6,000 raised to the 1/7 power, we end up getting that the base is approximately 3.465. All right, so then we need to put this together to write this function. So our final function is going to be P of t equals the initial value of 3 times 3.465 raised to the t power. All right, so then it says, you must present to the local city council about eradicating the snails. To make your point, you want to show the rate of increase per month. Convert your expression from being in terms of years to being in terms of months. Okay, so this is going to be a little bit weird, but if we take the formula we just wrote, which was P of t equals 3, and then it was times 3.465. Well, I need to break that up to be 1 plus so that I can get it back into that formula 1 plus r over n. So if it was 3.465, it's now going to be 1 plus 2.465 raised to the t, where we know that our compound formula would have been 3 times 1 plus r over n. And remember, it wants to know the increase per month, so that's r over 12 raised to the 12t. Going back to that formula that we've just learned. So pretty much what we have to do, as weird as this is we have to figure out how did we get from here to here. Notice on the outside I've got the t's there, I've got the 3's there. So I'm going to take this over here to the side so we can work this out. So 3.465, because that's really the number in here, is equal to 1 plus r over 12 raised to the 12th power. And we need to solve for that r over 12 so we can get that monthly rate. So just like we did above, if we want to get rid of raised to the 12th power, we need to undo it by raising each side to the 1/12. So in your calculator, you're going to type in 3.465 raised to the 1/12th power. And then we know that's equal to 1 plus r over 12. So if you pop that in your calculator, it's not very pretty, just leave it in there, but it comes out to be about 1.109. And that's approximately 1 plus r over 12. We would then subtract 12 from each side. We subtract 1 from each side, and we get 0.109 is approximately r over 12. Now, as weird as this is, we want to solve for r. But you got to remember that r is the yearly rate, and in this case, it wants us to describe the rate of the increase per month. So we actually are going to leave it right there at r over 12. As weird as this is, if you then change that back to a percentage, what that means is each month the snails are increasing by 10.9%. Had you multiplied each side by 12, it would have given you the yearly rate of appreciation, or how fast they were increasing per year, but we only wanted to know per month. Okay, so the last part. What is E? All right, so this is a special day when you're going to learn about a very, very special number called E. Just like you learned about pi back in middle school, and pi is this irrational number that we use to calculate circumferences and areas of circular shapes. We also have this very special number E. And E is the base that we use for quantities that grow and decay continuously. So what do I mean by that? So for example, let's say a squirrel dies. The squirrel doesn't decay once a day. It doesn't like all of a sudden hit midnight and go, oh, let me decay a little bit. That's not how it works. So things that naturally grow or decay in the world, they don't just decay or grow every hour. It's a continual process. And that's where E comes from. And it is a discovered number, just like pi was discovered by Archimedes in 3000 BC. E is a number that was discovered. So if you go in your calculators and you were to type 1 plus 1 over x raised to the x, and then you were to go to the table and look at really big values in the table. So like right now you can see they're around 2. So what I want to do is jump in my table. So I hit second window, and I'm going to jump to when x is 100. And then I'm going to go back to my table. Look at that where it's like 2.7. And then I'm going to jump in my table, because I don't want to scroll all day long, to when x is 1,000. And I go back and I look at those numbers. And then I'm going to go back in my table and I'm going to look when x is 100,000 or 10,000, or you can just keep making it bigger and bigger, whatever. And what happens is, what I'm trying to show you as x gets really big, in other words, as the amount of times you compound something goes towards infinity, which we can't substitute infinity in here, we start to see this number form that is e. And that's how e was discovered. Right here I've written on our notes this limit statement, and you're probably, what in the world is that? You'll learn about limits at the very end of honors pre-calculus and going into calculus, and I just like to throw it in here. But that is the definition of e. As n goes to infinity, the quantity 1 plus 1 over n to the nth power converges to e. All right, so let's look at this graphically. Since we know what y equals 2 to the x looks like, and we know what y equals 3 to the x looks like, graphing y to the e to the x is really easy, guys, because it's like right smack dab in between those two graphs. All you have to do to graph the function y equals e to the x, which is a very, very, very important function, we want to make sure you know how to graph these and that you recognize it, is we would still have the point 0, 1, because the y-intercept would be 1. Anything to the 0 power is 1. Then when I go to substitute 1, that would be e to the first power. Well, remember, e is about 2.7. So when x is 1, y would be about 2.7. When x is negative 1, it would be 1 over 2.7. So think about it. It would be smack dab between 1/2 and 1/3. So it would be about right there. And that's enough to get a good little sketch of y equals e to the x. You're going to want to learn this graph. The domain is all real numbers, negative infinity to positive infinity. The range is 0 to infinity. It's very similar to y equals 2 to the x, y equals 3 to the x. And the y-intercept is at 1. So make sure you've got that in your notes. You're gonna need that for later. And I would go ahead and put a big star and make sure you learn this graph. So if we take our compound formula that we learned at the beginning of this lesson, y equals a times 1 plus r over n to the nt, and we look at what happens as n approaches infinity. What happens, guys, is this part right here, this 1 plus r over n to the n, right there that I've just circled, it converges to e to the r. And that's where we get our compound formula. A lot of times we'll write it with the a and p instead, where a is our final amount and p is our principal. And I like to call it the PERT formula because it looks like it says the word PERT. A equals p e to the rt. So you hear me say all the time, anytime something grows continuously or decays continuously, we just use the PERT formula. If it grows, you have a positive rate. If it decays, you have a negative rate. So you might want to drop that down. Plus r, or positive r value when it's a growth, and a negative r value when it's a decay. Again, we only use this formula for when it is growing or decaying continuously. All right, last problem. Suppose that Keith has $1,200 to invest. His investment will earn an interest rate of 6.5% compounded continuously. Those are the key words. It didn't say monthly. It didn't say weekly. It didn't say semi-annually. It didn't say quarterly. It said continuously. So as soon as you see that word, that means it's being compounded every second of every day. So that's the n is infinity. And we can't substitute that into our compound formula. So we have to use this PERT formula. So I'm going to write that down real quick. As soon as I saw that, a equals p e to the rt. All right, the principal amount, or the initial amount, that was the $1,200. E is a number. We're going to put that in our calculator. The rate was 6.5%, so we're going to change that to a decimal, 0.065. So we're going to say raised to the 0.065. And in this case, the time is going to be 6 years. So we're going to say times 6. So in your calculators, you're going to type 1,200. And then right here on this first column, you're going to press second. I know this is weird. You see ln. It's actually natural log. We'll learn about it later. But above it is e to the x. So if you use that one, it goes ahead and puts e raised to. So then all you have to do is type in 0.065 times 6. And then press enter, and it'll give us our answer. And we're going to round to 2 decimal places. You also can get e by pressing second divide. You can see that little e right above that. That'll also give you e on your calculator. All right, so the next part. To the nearest tenth, how long will it take for Keith's investment to grow to $2,500? All right, so in this case, the question is how long? Make sure you look for those things. So we want to solve for time. We're under the same constraints. We're still initially having $1,200. The rate is still 6.5%, but this time we're going to be solving for the time. So if we write a function for this one, our original function would be the principal is 1,200 times e raised to the 0.065, but then it's going to be raised to the t. And since I'm going to put this in my calculator, I'm just going to write x, same thing as t. We want to know when it grows to $2,500, so in y sub 2, you're going to put in 2,500. And again, just like we did earlier, you're going to find the intersection. When you program these in your calculator, and you find the intersection, you get that x is approximately 11.3 years. Because this is a compounded continuously problem, that is your answer. You don't need to round up to the nearest year or the nearest quarter because it's being compounded every split second of every day. So our actual final answer here is that it would take 11.3 years. One of the things you're going to probably want to do to make sure you get these formulas down pat is write down each one. Y equals A times B to the X. Write down the basic percent growth and decay formulas. Write down your compound formula and your compound continuous formula, because you do need to learn these. They are not given to you on assessments.